So let's begin by reviewing 2x2 systems. 2x2 systems consist of two lines, or a line and a quadratic in the same plane. The solution to a 2x2 system is the point, or the xy coordinate, where the lines intersect. So we have a two-dimensional plane here, our x and y axes, and we have two lines that have a solution here, the point where they intersect. We can also have a line and a quadratic intersect, and the solution would be the point where they do so. Now we have two equations with two variables in 2x2 systems. So for example, this could be a 2x2 system. We have one equation and then a second equation, and they each have two variables. The variables have the same exact value in each equation. A 3x3 system is not much different. 3x3 systems have three equations, each of which has three unknown variables. So for example, x plus y plus z is equal to 4 could be equation number 1. X minus y minus z is equal to 3 can be equation number 2. And 2x plus 2y minus z is equal to -1 could be equation number 3. And for all three of these equations, each variable has the same exact value in each one. So throughout this chapter, we'll take a look at several different methods we can use to find the individual values of each variable for these equations. Now the solution to a 3x3 system is a little bit different than the solution to a 2x2 system. Since in a 3x3 system, we are working in three-dimensional space now instead of a two-dimensional plane. So 3x3 systems are three planes located in three-dimensional space, and the solution is the point, or the x, y, z coordinate, where the three planes intersect. So let's say we had one plane, this orange plane. We had a second plane, this green plane, vertically here. And then we have this blue plane perpendicular to the green one here. So we have three planes moving in three different directions in this space. And where all three planes intersect, that point right here, this would be the solution to this system. It is the only place where all three planes intersect. So for example, out here, only the orange and blue planes intersect on this side as well. And if we're moving up and down here, this is where the green and blue planes intersect. This point right here, we have the green plane existing, we have the blue plane existing, and we have the orange plane existing, and it's only in this one point. So when we can pinpoint a single coordinate in a three-dimensional space for a 3x3 system, that is what is considered the solution to the system. Now let's discuss a few scenarios that would create a lack of solutions. A 3x3 system does not have a solution if there is no single point, x, y, z coordinate, that lies in all three planes. So what are some of the scenarios that can produce this outcome? For one, if we have three planes that are all parallel to each other, then we don't have any planes that intersect. So this scenario would not produce a solution. We can have a scenario in which two planes intersect. So we have this plane here and this plane here that are parallel, so they never intersect each other. And then we have a plane that cuts through both. So here, two planes intersect. Here, two planes intersect. But there's no point where all three intersect, since this plane and this plane won't cross each other. And this is another situation where all three planes are crossing each other, but we don't have a place where all three intersect. So we have one plane coming down this way, one plane going towards the back, and another plane going horizontally through both. Here, the flat plane and this front plane cross. Here, the two vertical planes cross. And back here, our flat plane and the plane in the back cross. But there's no point where all three of these cross each other, so there would not be a solution to this system either. If a false statement is produced during the substitution or elimination method, then there are no solutions to the system. This is what we call an inconsistent system. So we'll get into the substitution methods and the elimination method in a moment, but keep an eye out for statements such as 0 is equal to 4, 0 is equal to -2, 0 is equal to 1. If you wind up with any of these kinds of statements, this is the indication that you do not have any solutions to this 3x3 system. Now on the flip side, there will be several scenarios that can produce an infinite number of solutions for 3x3 systems. A 3x3 system has an infinite number of solutions when two or more planes intersect at all points along a common line. So in this scenario, we have plane number 1, plane number 2, and plane number 3. And you'll notice they're all positioned in the same direction. They're all vertical. So now this allows for when they intersect, you have a line that goes infinitely north to south. These planes are not restricted to what you're seeing. They extend infinitely in all directions. So at this point here, you have an infinite number of points going north and south where all three of these planes intersect. So thus, there are an infinite number of solutions to this system. And there are several other scenarios that can produce an infinite number of solutions, such as two planes coinciding with each other. So they're the same plane. So here we have two planes that are the same, and they're intersecting another plane. Again, all of these planes are positioned the same way. So when they intersect, you have an infinite number of solutions. And you can also have all three planes coinciding. So in this image, it looks like these are stacked on top of each other, but this represents all three existing in the same exact place. And since all three of these planes exist in the same exact place, that lets you know that each point in the plane is a solution to all three planes. Thus, there are an infinite number of solutions in this scenario where all three planes coincide. Now, for infinite solutions, if a true statement is produced during the substitution or elimination method, then there are infinite solutions to the system. So this will produce a statement such as 0 is equal to 0. So if you wind up with a statement such as this one while you are doing the algebra, then you know that this is a system with an infinite number of solutions. So these are the different scenarios that we'll be encountering throughout the remainder of this chapter. Let's now begin discussing back substitution. Some 3x3 systems can be solved by substituting the value of one variable back into another equation to solve for an unknown variable. So let's say we have this 3x3 system here. Equation A is x plus y plus z is equal to 6. Equation B is 2y minus z is equal to 1. And equation C is z is equal to 3. Now, back substitution can be utilized when at least one of our equations provides us with the exact value for one of our variables. So since we know z is equal to 3, then we can substitute 3 in for z into either equation B or A for z. And when we do so, equation B has one unknown variable y, and equation A has two, x and y. So because equation B only has one unknown, we are going to solve equation B first. This will allow us to solve for y, and we already have z. And then we can substitute both of these variables into equation A to solve for x. So for back substitution, you take the equation that provides the value of one variable, and you substitute that value into the equation that has only two variables, the variable you are being given being one of them. And then you take those two variables and you plug it into the equation that has all three variables. And by the end of that process, you'll have the values for all three variables. So let's take this system and solve it step by step. You'll be asked to solve by substitution and check the answer. Equation A, x plus y plus z is equal to 6. Equation B, 2y minus z is equal to 1. In equation C, z is equal to 3. So step 1, substitute z into equation B here. And then step 2, solve for y. So when we plug 3 in for z in equation B, we get 2y minus 3 is equal to 1. And now to solve for y, we'll add 3 to both sides, giving us 2y is equal to 1 plus 3, which is equal to 4. And now to remove this coefficient of 2, we'll divide both sides by 2, giving us y is equal to 4 divided by 2, which shows us that y is equal to 2. So once we substitute z into equation B and solve for y, we have 2 of our 3 variables solved for. So to find x, we want to substitute y and z into equation A and solve for x. When we do so, we get x plus 2 plus 3 is equal to 6. 2 plus 3 is equal to 5. And now we can solve for x by subtracting 5 from both sides, showing us that x is equal to 6 minus 5, which is 1. So now we have the value for each of the 3 variables. X is equal to 1, y is equal to 2, and z is equal to 3. So this x, y, z coordinate would be the solution to this 3x3 system. And you want to check your answer by plugging the x, y, z, 1, 2, 3, into the original equations to make sure that you get a true statement for all 3. So when we plug in 1, 2, and 3 for x, y, and z into equation A, we get 1 plus 2, which is 3. 3 plus 3 is equal to 6. So since we get a true statement, 6 is equal to 6, that confirms that x, y, and z have the correct values. For equation B, we have 2y minus z is equal to 1. 2 times 2 is equal to 4. 4 minus 3 is equal to 1. 1 is equal to 1 confirms that these are the correct values for y and z. And for equation C, we know that z is 3. 3 is equal to 3 is a true statement. So this confirms that we found the correct values for x, y, and z for this 3x3 system. So that is how you utilize the back substitution method to solve a 3x3 system. Let's now have you complete a few practice questions. Solve by substitution and check the answer. Question number 1, equation A, 2x minus y plus 3z is equal to 11. Equation B, 2y minus 2z is equal to negative 14. And equation C, z is equal to 4. Question number 2, equation A is negative 4x plus 2y minus z is equal to negative 15. Equation B, negative 5y plus 2z is equal to negative 12. And equation C, y is equal to 2. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, step 1, substitute z into equation B here, and then step 2, solve for y. So when we plug in 4 for z here, we wind up with 2y minus 2 times 4 is equal to negative 14. Negative 2 times 4 is equal to negative 8. And now we can solve for y. So we'll add 8 to both sides, showing us 2y is equal to negative 14 plus 8, which is equal to negative 6. And now we'll divide both sides by 2, showing us y is equal to negative 6 divided by 2, which would be equal to negative 3. So after solving for y, we know y is equal to negative 3 and z is equal to 4. So now we want to substitute both of those values into equation A and then solve for x. So when we do so, we get 2x minus negative 3 plus 3 times 4 is equal to 11. And that would be equal to 2x plus 3 plus 12 is equal to 11. 3 plus 12 is equal to 15. So we wind up with 2x plus 15 is equal to 11. And now to solve for x, we'll subtract 15 from both sides, showing us 2x is equal to 11 minus 15, which would be negative 4. And to remove this coefficient of 2, we divide both sides by 2, giving us x is equal to negative 4 divided by 2, which would be negative 2. So now we've found x, y, and z for this system. The solution would be x is negative 2, y is negative 3, and z is equal to positive 4. And to check the answer, we want to plug the x, y, z, negative 2, negative 3, and positive 4 into the original equations to make sure we get 3 true statements. When we plug them into equation A, we get 2 times negative 2, which would be negative 4, minus negative 3, which would be plus 3, plus 3 times 4, which would be positive 12. Negative 4 plus 3 would be equal to negative 1, and negative 1 plus 12 is equal to positive 11. And since we wind up with the true statement 11 is equal to 11, that confirms that these are the correct values for x, y, and z. So now we move on to equation B. 2y minus 2z is equal to negative 14 would give us 2 times negative 3, which is negative 6, minus 2 times 4, which would give us minus 8. Negative 6 minus 8 is equal to negative 14, giving us the true statement, negative 14 is equal to negative 14, confirming that these are the correct values for y and z for this equation. In equation C, we know is correct, 4 is equal to 4. So this confirms that we did find the correct solution to this system. X is negative 2, y is negative 3, and z is equal to 4. And now let's have a look at question number 2. We were given equation A, negative 4x plus 2y minus z is equal to negative 15. Equation B is negative 5y plus 2z is equal to negative 12. And equation C is y is equal to 2. So step 1, substitute y into equation B here. And then step 2, solve for z. When we plug 2 in for y here, we get negative 5 times 2, which is negative 10, plus 2z is equal to negative 12. And to solve for z, we'll begin by adding 10 to both sides, giving us 2z is equal to negative 12 plus 10, which is negative 2. To get rid of the coefficient of 2, we divide both sides by 2, showing us z is equal to negative 2 divided by 2, which would be negative 1. So now we have y and z, so we just need to find x. So step 3, substitute y and z into equation A. And then step 4, solve for x. When we do so, we get negative 4x plus 2 times 2 minus negative 1 is equal to negative 15. 2 times 2 is 4, minus negative 1 would be positive 1, and 4 plus 1 is equal to 5. So we wind up with negative 4x plus 5 is equal to negative 15. And to solve for x, we'll now subtract 5 from both sides, giving us negative 4x is equal to negative 15 minus 5, which would be negative 20. And to remove the coefficient of negative 4, we divide both sides by negative 4, showing us x is equal to negative 20 divided by negative 4, which would be equal to positive 5. So the solution to the system would be x is 5, y is 2, and z is equal to negative 1. And now step 5, check the answer by plugging the x, y, z, 5, 2, -1 into the original equations. When we do so, we get -4 times 5, which is -20, plus 2 times 2, which is +4, minus -1, which is +1. 4 plus 1 is 5. -20 plus 5 is -15. So the true statement, -15 is equal to -15, confirms that x is equal to 5, y is equal to 2, and z is equal to -1 for equation A. For equation B, we have -5 times 2, which is -10, plus 2 times -1 is -2. -10 minus 2 is equal to -12, providing the true statement, -12 is equal to -12, confirming that these are the correct values for y and z for equation B. In equation C, we know is correct, 2 is equal to 2. So we found that the solution to this 3x3 system is x is equal to 5, y is equal to 2, and z is equal to -1.